Question number 26 is a beautiful example of applying Newton's third law. It goes quite beyond our regular normal force of friction, force of gravity type of examples, because this involves also a magnetic force between two magnets. But Newton's third law says every action has an equal and opposite reaction. So we have the attraction between the upper magnet and the lower magnet. And see how they tell us that the lower magnet on the upper magnet applies 6 newtons. That means that it's going to be 6 newtons the other way around. So the upper magnet on the lower magnet is also going to be 6 newtons because they cannot attract each other with different forces. Let's start with the lower magnet. The lower magnet will obviously have force of gravity applied to the center. So I'm going to draw it straight down right here. And they mention that each magnet's weight is 2 newtons. So, and then they also say the magnetic force is 6 newtons. This is going to be the weight. So I'm going to say mg, and that is 2 newtons attracted to the upper magnet. So I'm going to draw an upward force, and should be rather bigger than. So this is, I'm going to say force magnetic. As a result of that magnetic force, it's pressing into the table, and the table is pressing back. So that is a normal force. This normal force is not the usual upward. This is a downward normal force. For Newton's first law to be applicable here, because our magnet is staying in place, all forces on that magnet should be equal. So I'm going to say force magnetic should be equal to mg plus the normal force from the table. Let's go for the upper magnet. Again, it's going to have our 2 newtons downward, which is mg, the same magnetic force that is now downward for this one. Because of that magnetic force that is attracting that magnet to the table, it's going to be pressing into the table. So the weight is pressing into the table, and the magnetic force is pressing into the table. So therefore, the normal force from the table is going to be equal to those two. Good luck to me. So force normal, that equals to mg plus force magnetic. Now, our poor baby table here. It has its own force of gravity, mg, which is an enigma for us. We don't know how big it is. So force of normal upper is provided by the table. So therefore, it's going to be an equal force into the table. In other words, that force, this force magnetic, and that force mg together provide this force right here. This force by the upper magnet onto the table. I'm going to write it like that. They ask us to do dashed lines to connect the members of the action-reaction pairs. Dashed, boop, 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 boop. These are action-reaction forces. The table is supporting the magnet is pressing into the table. Another action-reaction, boop, 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 boop. These two magnetic forces are action-reaction. What else am I missing? I am missing for the table, boom, boom, this will be force normal from the lower, and that's your boop, 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 action reaction. So magnet presses into the table presses into the magnet. And I am missing one more, the force from the floor onto the table, which doesn't have any pairs. It's just the normal force from the table, from the floor. Okay, so F. And they're asking us for the lower magnet push into the table, this little force by the lower, right there, Fn from the lower, which will be force magnetic minus mg, is just 4 newtons.